Okay, listen in please, Katie. So, after watching our video on the right, which explains spectrometry and where the spectroscopes are used, what we should be able to realise is that when you look at the sun is made of different gases. Okay, let's say we've got the sun here, and the sun emits lots of light, which we're familiar with. Now there is gases between us and the sun, different gases, okay, represented by different colours. And these gases absorb certain wavelengths of light. By looking at the sun and looking at the spectrum and observing which elements are missing, we can tell what gases are there. So, when you looked at the spectroscope and you looked outside at the sky, you seen what you appeared to be the rainbow, didn't you? The sort of red, green, orange, yellow, blue, purple, violet. When you looked at the gas lamps, which only emitted one gas and had one wavelength of light, you didn't see the full spectrum, did you? No. So, what you can tell is not only the temperature, but what the star is made of. If you turn a bulb on, its temperature increases, and more light emitted at the blue end of the spectrum. Okay, the hotter it gets, the more blue the light that it emits. Violet light has a smaller wavelength than red light. As the temperature increases, the wavelength of the light emitted becomes shorter. So, if something's hot, it's brighter at the blue end of the spectrum. Okay, if we look at this little diagram here, that's blue, that's red. The hotter it is, the brighter the blues would be. The cooler it is, they would be not as bright. If you've got 4 stars and you have to rank them in order of which star has the greatest temperature, what do you think would be the hottest star there? Correct, that would be the warmest. The yellow would be the second warmest, orange, red, in that order. So you can tell how hot a star is by the colour of gas that it emits. So light often comes from objects which have heat, energy, the sun, a lamp, a TV. Light is produced in the same basic way, giving energy to atoms. Okay, just turned over the page, sorry. You should know how to label and draw an atom. You have the nucleus in the centre with protons and neutrons and electrons orbiting. If an atom is given the right amount of energy, an electron can jump up to a slightly higher energy level. After a short time, it falls back down to its normal energy level. As it does this, the extra energy is released as light. A small jump gives it a small amount of energy. A large jump gives a large amount of energy. Have you done this? Who does chemistry out of you guys? So have you done anything about electron shells? So you know a little bit about electrons are found in different areas. Depending where they are, they have less energy or more energy. So if you have an electron, let's say, and it's orbiting and it has a certain level of energy, let's say it has energy level 1. You give it more energy, it can jump up to orbit up at here, let's say energy level 3. You take away the energy you're supplying, the extra, it just falls all the way back down. In doing so, when it reaches its original state, the energy it gained is given off as light. That's the pen battery playing up again. Okay, as light. So, you lift the electron up in energy level. When you stop holding it there, it falls back down and gives off light. Nicholas. Do it with multiple electrons. How do you give them energy? Apply a voltage. Okay, that's a simple way to do it. You put a voltage through a material, electrons have more energy, that material heats up, those give out light. You do more on this in 5th year in the semiconductor topic. And we'll just finish with this just now. So if you take a prism and you shine white light through the prism, what comes out the other side appears to be what you up until today would call the rainbow, but now you're going to call it the visible spectrum of light. This is the light that you can see with your eye, the human eye. It can see a range between 400 and 700 nanometers. Outside of that, what do you think we would name the wavelengths and frequencies of light? Correct, infrared, ultraviolet. So it's to do with the 3rd year booklet, electromagnetic spectrum. White light consists of different colours, each with a different wavelength. The prism acts in a way which refracts the light and makes them bend and change their direction. Red light changes a different amount to violet. Many light sources produce a continuous spectrum containing all the wavelengths of visible light. An example of this is a standard light bulb. All atoms give off light when they are heated. The atoms of any particular elements give off large quantities of radiation. As a result, the spectrum of that element has bright lines. Line spectra can be produced in the lab using sodium or neon lamps, which you got to look at today. Okay, you looked at sodium lamps, you looked at mercury lamps. Okay, so you take your spectroscope, you point it at the vapor lamp. Each element has a pattern of spectral lines that differ from any other. So if you imagine the visible spectrum, okay, let's say you had your visible spectrum. And as we know, it goes from red all the way through to violet, and all the colours in between. When you look at certain light sources, there are black lines which appear like a barcode of different thicknesses at different positions in the spectrum. And what that tells you is that those wavelengths of light have been absorbed. So different barcodes, you could call them, of light that's missing from the full spectrum tells you different elements are present. So how do we use this to identify what's in a star? If we take the spectrum of a star, astronomers can work out the gas that is present in the star. Use the spectral lines to identify what gas is present here. So we've got figure 1, and this would be your full visible spectrum. Now there are these black lines to replicate areas where the light hasn't made it to your eyes because that wavelength's been absorbed by the gas. Which gases do you think have absorbed light in figure 1? Let's have a look. So we've got a black line there, there. Hydrogen works, correct. And the other one we've suggested is sodium. Let's have a look. So sodium has 1, 2, 3, 1, 2, 3, 1, 2, 1, 2. Okay, so we've identified, and we didn't even need to look at it in colour, that the elements present are hydrogen and sodium. The absence of light where the black lines are tells you hydrogen sodium has absorbed all of the wavelengths. During the lifetime of a star, a nuclear reaction takes place within the star in which lighter elements are fused together. Which elements would be very prominent in a young star? we would have lighter elements, which are hydrogen, helium. These two would react with each other. So that'll do us for today. Any homework will be put on Firefly. Just for your information, if you look at the page below, there's some colour diagrams which we'll talk about next period.